I'm Anna O'Donnell-Luria, and you'll be hearing today from Samantha Baxter and myself on Can the Prevalence of DADA2 be estimated? And I just wanted to shout out that this came from a talk that we gave through the Chan-Zuckerberg Initiative to the RARES1 cohorts, where Chip Chambers and Pri Lee reached out to us afterwards to see if we could help them answer this question. So the power of 7.5 billion people on the globe is that given the known mutation rates, it is almost certain that every possible single base change compatible with human life exists in a living human today. And there's a lot of opportunities to bring all that sequence data together and learn what genetic variation is possible and tolerated in humans. Over 2 million people, probably well over by now, have been either exome or genome sequenced. However, most of these are happening in smaller research studies where the data is siloed in individual projects. And there's a lot of difficulties moving these very large data sets. They're all consented differently, and so there's challenges of bringing them together because of inadequate data use permissions. And everyone handles their data a little differently, so it's processed differently, variants are called differently, so you can't necessarily bring the data together easily. So at the Broad Institute, we've created some aggregated databases to try to help the community have these large human reference databases of human genetic variation. The first we launched in October 2014 and work led by Daniel MacArthur, and it was called the Exome Aggregation Consortium, or EXAC, and had 60,000 exomes. We followed this in 2016 with the Genome Aggregation Database, or GNOMAD, which is what we'll be focusing on today, which has 125,000 exomes and 15,000 whole genome sequences, all done on Build 37. And we have a newer data set that we've just released an updated version of this October, actually, but originally released in 2019, the GNOMAD v3 that has over 76,000 genomes. The graph is showing you how many users combined weekly access the GNOMAD browser to look at this data, and over 30 million people from 184 countries have used this data to date. You'll also notice from the graph that there's a lot less research going on over the winter holidays. So that's another trend we've picked up. And all the clinical diagnostic testing pipelines now for molecular diagnostic testing are using these data sets. Data sets include short-read Illumina sequence data, primarily from case control studies of complex adult onset diseases. So these are things like type 2 diabetes, heart attacks, migraines. Data sets are depleted as much as possible of people known to have severe pediatric disease, or if someone's recruited as the parents in a rare disease study, we would not include the parents in the GNOMAD data set either. Individual level data is not shared and phenotype data is not available. As I mentioned, there's lots of different data use permissions, so we have permission to aggregate and share the aggregate data, but not individual level. It's pretty evenly split between male and female, and the mean age is 54 years. We've pretty good diversity in these data sets. You will notice that European populations are vastly overrepresented in these data sets, but there are many other ancestries, including reasonable size from African, Latino, Ashkenazi Jewish, East Asian, and South Asian represented. So I'll be talking about the GNOMAD v2 data set for most of this talk. So I'm a clinical geneticist. I access this data not through the giant VCF that we release from it, but through the GNOMAD browser. And I'm just showing you the ADA2 gene here. To orient you, this is the exons of the ADA2 gene. So the gene is not drawn to scale here, but if you clicked on the region view, it would show you everything. You can see the little blue mountains are the exome data, and the green flat coverage is the coverage in the genome data. So we have good coverage over all the exons of this gene. Below we have, not necessarily in GNOMAD, but we've highlighted the variants that have been called pathogenic or likely pathogenic in ClinVar, a clinical database. And then below, these are the variants that we see in GNOMAD, with the height of the peak representing the more common variants. And they're colored according to the type of variants they are with the color scheme here. And then if you go down below, you'll see a long list that is every single variant we see in this gene, the consequence, for example, amino acid change, the type of annotation, so missense or synonymous change. The allele count is the number of times we see this variant. The allele number is the number of number of chromosomes, not people, chromosomes genotyped at that site. And the allele frequency is the allele count divided by the allele number. We also note how many homozygotes we see. So you can click on any one of these variants and go to the variant page. And what you're seeing here is some summary statistics about this variant up top, some in silico predictors, but I really want to focus on the heart of the page here, which is the allele frequencies in different ancestry groups. And so you'll see this variant that I've selected to highlight here is present in 115 of African or African American ancestry. There's the rounded age distribution for carriers of this variant. There's other QC stats that you can find on the website. And you can actually open up the triangles next to the different ancestries. And for some of the ancestries, not for all of them, we have some subcontinental ancestries present, and these will increase over time as representation in these data sets grow. The other thing is if you were to scroll down the page, you can see the read data that supports the variant being called. And so you can take a look and make sure that the variant looks real to you. But there also is a lot of QC that's done on the data, and that will tell you whether the variant passed QC or not, along with some links to UCSC and ClinVar. So I just want to show you the idea of using it for detecting or estimating the number of carriers in the population for a specific variant. I'm using the classic CFTR phenylalanine 508 del, the most common cystic fibrosis carrier variant in European populations. We know from carrier testing that 1 in 41 Europeans is a carrier for this specific variant. About 1 in 25 Europeans is a carrier for cystic fibrosis. And so if we take the number of chromosomes divided by 2, get the number of people of European ancestry in this NOMAD data set, 1 in over 41 is the number we expect to be carriers. We get 15,043. And so when we look at that, we see 15,098. So it's working pretty well to estimate the number of carriers in the population in NOMAD, using NOMAD. And just as highlighting an example of how different ancestries have different carrier frequencies, the allele frequency of this variant is 1.2% in Europeans, but is actually, this variant is never seen in the about 10,000 East Asians sampled in the NOMAD data set. And then to show you just further why we can't just count up the number of affected people in this data set. Again, I told you these are case control studies from adult onset conditions, so they should be depleted for people with rare disease. Looking still at this CFTR variant, we actually expect to see 9 people who are homozygous for this variant. We see 1. They're actually a control in a data set. So it's possible that someone with rare disease slept through. It's also possible somebody with who's not penetrant for cystic fibrosis, and potentially interesting to study further down the line, is in this data set. But it highlights that you can't just count up the number of homozygotes. And we also don't have compound het estimates because we don't have trios for this data. So I think this data set is really powerful for detecting carrier frequencies and taking those carrier frequencies into prevalence estimates for recessive conditions. And with that, I will hand it over to Samantha Baxter to walk you through how we do this.
Great. Thank you, Anne. So I'm Samantha Baxter. I'm a genetic counselor at the Broad Institute, and I run our variant curation team. And I will be walking you through our aggregate frequency analysis that we performed for data 2. This is a process that we've developed over the last couple years, where we're able to use variant databases such as NOMAD to estimate the disease prevalence for recessive disease conditions. Next slide, Anne. Great. So step 1 in estimating carrier frequency and thus disease prevalence is actually establishing a list of likely pathogenic and pathogenic variants in the target genes of interest. So as Anne walked you through, for ADA2, we're able to get this full list of variants out of NOMAD. And then we were able to work with Dr. Lee's group at Children's Hospital Boston to filter down that list to the ones that that he suspected are most likely to be pathogenic. And so these are variants that have been reported at least once in the literature in individuals with DETA2. And from there, we are able to take the final list of variants that we can bring forward to calculations. Next slide. So we were provided 57 variants by Dr. Lee. 8 were loss of function. So this means either start loss variants, insertions, or deletions in the sequence. And then we had 49 missense variants, so single nucleotide changes. One variant that I wanted to call out, which we'll talk about throughout this presentation, is the phenylalanine 355 leucine variant, or F355L for short. And this is a variant that has only been reported in one individual in the literature, but it has study showing that it has reduced activity to about 50% of normal. Now, if we brought this through the full variant curation process that we typically run within our group, using guidelines set forth by our community in 2015, it would probably come out to be a variant of uncertain significance, or a VUS. However, there is suspicion that perhaps this variant is leading to disease in some individuals. And so I wanted to use this variant to highlight how even one variant, if it's at a high enough frequency, can really influence the final carrier frequencies and disease prevalence, both for all populations, but also for very specific subpopulations, like Anne mentioned previously. So as I mentioned before, the selected variants were reported in at least one individual in the literature, and ultra rare variants that have not yet been identified in patients were not included in this process. Next slide. So once we have that established variant list, we're then able to move forward and calculate the aggregate carrier frequency and therefore prevalence. Next slide. So I did want to take a quick step. Anne had mentioned that, or a quick moment to explain, Anne had mentioned the subpopulation, all populations, but then also the global populations and subcontinental populations. Those populations are genetically determined. These are not self-reported populations when I refer to them throughout the rest of this presentation. So what we did perform this analysis across all populations within NOMAD, as well as these global populations and subpopulations as well. Next slide. For the mathematical part, we applied a well-established principle called the Hardy-Weinberg equation. This is an equation that can be used to calculate the genetic variation of a population, but it does assume Hardy-Weinberg equilibrium, which means that the amount of genetic variation in a population will remain constant from one generation to the next. So this is a known limitation and an assumption that we take whenever we apply this equation. Also, for rare disease, P is so close to 1, and when I say P, that's referring to our reference allele, or what can be called normal allele in some terms. And because it can be assumed to 1, we actually modify the calculation, next slide, where we just use Q as the aggregate allele frequency of likely pathogenic variants. 2Q is our carrier frequency, and Q squared is our disease prevalence. Next slide. And this is the part I hope you are all excited for. It's our results. So I will call your attention first all the way to the left in the dark blue. And this is the carrier frequency for all populations in NOMAD. And we get about 1 in 280, 1 out of 283 to be exact. I will go over sort of all the different populations and specific trends a little further in the presentation, but I just wanted to call your attention to the East Asian population for the purposes of this slide. So as you can see in the title, this is the carrier rates without that 355L variant. The reason I want to call this out is because this variant is far more prevalent in the East Asian population. Actually has a carrier frequency about 1 in 170 on its own. And so without that variant, the carrier frequency for the East Asian population is about 1 in 1,000. And if you go to the next slide, you can see that the impact on the carrier frequencies is very obvious right off the bat in the East Asian population. So like I said, it went from about 1 in 1,000 to about 1 in 150. As well, the carrier frequency for all populations went from about 1 in 280 to 1 in 250, and very specifically driven by this increase in the East Asian population. So going on, so carrier frequency again is 2Q. Then we, to calculate the prevalence, we go to Q squared in the next slide. And this is the prevalence. Again, I did this without the 355L variant. And you can see that the prevalence is about 1 in 320,000 individuals across all populations. And again, I want to just call out the East Asian population. I'll get to the other ones as well towards the end, like I said. The East Asian population without the 355L variant is about 1 in 4.3 million individuals. However, if we then include this variant, next slide, you can see that it goes significantly up on the bar chart, and actually increases to about 1 in 92,000. And the overall frequency goes to about, or the overall disease prevalence goes to about 1 in 250,000. So you can see that even one variant, if it has a high enough frequency, can have a huge influence on the final calculations that we apply or that we use. Now, we think that there is some evidence to show that this variant is disease causing, and the VUS classification comes from this gold standard classification process that we apply. But I think it shows that even if a variant is not likely pathogenic or pathogenic, this process can show us the variants that are really rich for a specific data set or specific ancestry to dive in and figure out the functional effect. And that can really then drive where appropriate genetic testing can be targeted. It can influence the way that genetic counseling is performed. And so we really thought that this was a nice story to call out. Next slide. So this is another piece of data that we give with a lot of caveats for a few reasons. But we know that it is the number one question that everybody has. Once I have the disease prevalence in NOMAD, can I just apply this across the world population and come up with the estimated number of individuals? And certainly we can do this mathematically. I've done it on this slide, but I do want to call out that NOMAD is not representative of the entire world's population. And therefore, this number is only a rough estimate. Certainly there are populations that are missing. We don't have the Middle Eastern population well represented, and other types of populations. And so I really just want to caveat this with all of those. But that being said, I again broke it down with and without the 355L variant. So without the 355L variant, we can expect about 24,000 individuals globally to have data to. With this variant, we would expect, my apologies, that number to go up to 31,000. Next slide. So takeaway points. I didn't want to just focus on the East Asian population. There were a lot of other great trends that came out of this as well. But I did want to just bring back that the carrier frequency across all individuals in NOMAD is 1 out of 283. The disease prevalence across all populations is about 1 out of 320,000. Again, I provided those numbers adjusted for including the 355L variant as well beneath there. There were a few subpopulations that have lower prevalence. But the way that we look at these numbers is slightly different depending on the context. So in a well genetically studied population, such as the Ashkenazi Jewish population, we see a prevalence of about 1 in 107 million. We know that this is a bottlenecked population. We know that they're well studied clinically as well represented in NOMAD. So we feel very confident that this is actually showing that this disease is significantly less prevalent in this subpopulation. However, you'll see in the African population that we see a disease prevalence of 1 in 2.3 million. However, this is a population that we know is not well studied and is not well characterized in NOMAD. And therefore, we think it's more likely that what this is showing is that we haven't yet found the disease-causing variants for DATA2 in the African population. So a few subpopulations have a higher prevalence, specifically the Finnish population. Now, this is another bottlenecked population. It also, this increased frequency is driven strongly by an established pathogenic variant. And so we feel that this is actually truly representative of a higher prevalence in this community. I've talked a lot about the East Asian population in my talk so far, but I did just want to highlight again that this phenylalanine 355 leucine variant really is a big driver in being able to come up with a classification and figure out if this is a hypomorphic allele, if it needs to be seen in combination with another more pathogenic allele, or if the actual homozygous individual could have DATA2, really is a rich area for research. And we're excited to work with Dr. Lee on trying to provide additional information that may be helpful for that. Next slide. So I did just want to call out a few of the limitations. We did only include variants that were present in NOMAD. There are some likely pathogenic and pathogenic variants that are out there in the literature that just aren't in NOMAD and therefore didn't influence our numbers. Some populations are missing from NOMAD, as I mentioned, specifically the Georgian Jewish population, which is known to have a 1 in 10 carrier rate for DATA2. This calculation does not take into account the increased rates of consanguinity in some cultures. So next steps are to expand into NOMAD version 3.1, which has added diversity over the version 2.1.1 that we used for these calculations. We would also like to continue working with Dr. Lee's group to add in functional study information and additional potential variants that we could expand upon. And longer term, we'd like to create an online calculator that would allow ongoing recalculation when new information is learned either about a classification or more frequency data. Next slide. And finally, we'd just like to say thank you to everybody. We have a large group at the Broad Institute with lots of people's pictures here. This is a group effort. Obviously, both Anne and Dr. Lee work at Children's, and we appreciate them for their help on this. And the Chang-Zuckerberg Initiative and the RARE is one group, and obviously the DATA2 community for having us come talk today.